Here is our lab17 homemade op-amp, which we built up stage by stage in the previous video. I'll give you a tour of each part of that in a moment. So here is what we built. First stage is a differential amplifier whose differential gain is about 24. And we put this current source in place of the tail resistor, which makes this denominator very large. So then we have a common mode gain on the order of 10 to the minus 3 with a minus sign, but it's so small we can't even measure it with our setup. And then we have that was stage 1. Stage 2 is this common emitter amplifier. The one thing that looks funny about it is that it's upside down because we used a PNP transistor following Tom Hayes's example from Learning the Art of Electronics, a book I highly recommend. And then another little trick here is we took advantage of this thing called the Miller effect, which we do not talk about at all in this course, but it is an effect of negative feedback in amplifiers. And the result is that this tiny little capacitor, we put a 100 picofarad capacitor between the base and the collector, and it actually behaves like a much bigger capacitor in killing the high frequency gain because of the gain of this stage. So stage 2 has a gain of minus 20, at least calculated gain. So that gives us an overall calculated gain of 480. We actually measured more like 250, but anyway, it's big enough to be useful. And then we have this push-pull output stage. Its purpose is to reduce the output resistance of the overall op-amp. So without the push-pull stage, the output resistance of this overall op-amp would be roughly comparable to this collector resistor, 6 kilo ohms. But the presence of this push-pull output stage should be able to reduce that by a factor on the order of beta. So it should be basically tens of ohms output resistance instead of a few kilo ohms. Actually, one thing I forgot to draw in this diagram at the end of the previous video, and I actually got some kind of squirrely behavior when I wired it up without this because it wasn't on my diagram, is there is some kind of resistor. It doesn't really matter what value precisely, I think, but this is on this diagram in the lab handout. There's a 10K resistor to ground, so the push-pull was not really behaving sensibly when we weren't drawing enough current, I think, to keep these transistors active. So I think the scope probe was too big a resistance to keep these transistors active. So 10K gets enough current flowing. So in the tests at the end of the previous video, I actually put this 10K resistor to ground, but I didn't show you that I had done that. Okay. Now, though, what's wired up is this is set up as a times 11 inverting op-amp configuration, non-inverting, times 11 non-inverting. So remember, the inverting configuration, the non-inverting configuration of the op-amp looks like this. Here's the input, here's the output, and then the easiest way to understand how this works is you see, feedback tries to make these two things equal. And this point here is 1/11 of V out, right? So this is basically V out times R1 over R1 plus R2, which in this case is V out over 11. So V in is V out over 11, therefore V out is 11 times V in. So we have this wired up as a times 11 non-inverting amplifier. How did we do that? So instead of connecting this to ground, this 10K resistor, and here, let me label it in a way that's a little bit more obvious. So here's 10 kilo ohms, and it goes to the inverting input, which is pin 1. Okay, so this is in minus, and this is in plus. Okay. So remember, before we added the gain stage, this was in minus and this was in plus. But then the gain stage flips the sign. So you change which one is plus and which one is minus, which one's the inverting, which one's the non-inverting input. So this went back to here. Okay. And then then we have 1 kilo ohm to ground. And our output is here. And let's see what that looks like on the scope, and then we'll see what it looks like as built. So, okay. Here it is on the scope. And the green trace, channel 4 of the scope, is our input signal. And our input signal, actually we're only using one channel here. So in fact here, let's just disable channel 2. Yeah. And okay. So our input signal is a 500 millivolt amplitude sine wave at 1 kilohertz. Oh no. What? Run. Okay. Okay. So, and then you see it over here. Everybody here is 2 volts per division. So you see channel 4, 2 volts per division. There's this, you could say that's plausibly a half volt amplitude. And then everybody else is bigger. Let's change channel 4's scale to 200 millivolts per division. And now you can see, okay, it's a little smaller than the output, so it seems like the output is multiplied by a factor a little bit more than 10. Then, if we look at channel 3 here, the magenta trace, that looks like it's a little more than 10 times as big as the input signal. And remember, this result that V out is 11 times V in is absolutely true in the limit in which the open loop gain of the op amp goes to infinity. And our open loop gain is not quite infinity. So I think that accounts for the fact that this gain is a little bit less than 11. It's probably more like 10 and a half instead of 11. Okay, so that is the output of the op amp overall. And then channel 1 in yellow is the output of stage 1, the differential stage. So that's kind of fun to see. And you see it has the opposite. Oh, what? Oh, yeah. It has the opposite sign because it's before the gain stage. Good. Okay, I got confused for a minute. So here, you can't see the differential stage before it, but this is the output of the differential stage, the input of the gain stage. The gain stage flips the sign, so we expect the output of the differential stage to have the opposite sign, so it does, okay? And remember, it's offset from 0 by about 8 volts, which we remember from the previous video. And, okay, that's cool. And then if we look at channel 2, Channel 2 is the output of the gain stage, so it's just before the push-pull. And remember, our favorite feature of the push-pull is crossover distortion, where if you have an input signal that looks like this, then the output of the push-pull will look sort of like this, where it doesn't turn on and it stays like, so now the NPN is on, the PNP is off, and now the PNP is on, the NPN is off, and now they're both off, and then the NPN is on, the PNP is off, and so on. So you get these little horizontal flat spots. Now op-amp feedback wants to remove those, and we saw this in the push-pull lab. So op-amp feedback then undoes the distortion. And the way it undoes it is it makes the previous stage's output have little vertical things, so that then the diode, whoops, that's not right. Then the diode drops bring us back to the original undistorted curve, like this. So then the output now should perfectly follow this intended yellow curve. And then we see that, so that's kind of neat. And we see that in these traces because when we look at the output of the gain stage, which is the input of the push-pull, so we look right here, which is what the blue or cyan trace, channel 2, is looking at, you see these little jumps. So basically, when the NPN transistor is on, the output of the gain stage is a diode drop higher than the desired output. And when the PNP stage is on of the push-pull, there's NPN and there's PNP of the push-pull. When the PNP half of the push-pull is on, the output of this gain stage is a diode drop below the desired output. So you see that the cyan, or kind of light blue curve, it's a little too high here, and then it's a little too low here, and it's a little too high here. And that's perfect because it is exactly undoing then what the push-pull does. So then the magenta signal, which is the output of the whole op-amp, has the nice sinusoidal shape that we want. So that's fun. Okay, let's do a little tour of what we built. So do that. I hope I can remember what everything is here. Let's see. It's kind of a rat's nest. This is like much more crowded than usual. Well, one thing we can do, we can start, okay, on the left. So the left is this current source that we made for the tail over here. And remember, this transistor is EBC. So at the emitter, we should have a 1K to -9 volts. So from the emitter, we have this resistor going to -9. So this is our 1K resistor to -9. And then the base, EBC. So the base is in the middle. So from the base, we have 3K to ground and 1K to -9. So here's the base. So we have 3K to ground. Yeah, it begins with orange. That's right, 3K to ground. And we have 1K to -9. And then the collector has this little blue wire going over to this thing, which is just to the left. It's just to the lower left of pin 1 here. So this little column just to the left. No. Sorry. It used to be off to the left where I had the 200 ohm resistors. Those are gone. So it's going to pin 2 and it's also going to pin 4. Yeah, so this collector should be going to pin 2 and to pin 4 of the integrated circuit. So here it is going directly to pin 2, and then there's a little jumper from pin 2, a little blue jumper from pin 2 to pin 4. Okay. And then remember, this is our CA3096 transistor array. Okay. Then, so that's the current source over on the left. And I guess we can go around this circuit pin by pin. So pin 1 is the base of this transistor, and it is our inverting input. So it should just be this wire coming from between these two resistors. And that's what we have here. You see, so pin 1 is just this wire, which is coming from between these two resistors, which is our op-amp feedback network. Then pin 2 is the emitter of Q1, and we said, so we saw the little jumper over to pin 4, and we saw the jumper over to the collector of this current source. So we talked about that. Pin 3 is the collector of Q1, so it just goes up to +9. So let's find that, yeah. So here we have pin 3 has this red wire. I usually use red for power. So this red wire goes up to pin +9 volts. Then pin 4, all it does is it jumps over to pin 2, and we saw that already. That's this blue wire. And then pin 5 is the base of Q2. So that is my non-inverting input. So that's my signal source. So what should be plugged in there is my signal source. So pin 5, so here is my signal source from the EE board waveform generator, and that's going into pin 5. And it's way down at the bottom, so I can plug it and unplug it without getting too confused. And then pin 6 is the collector of Q2. So it goes two places. One is it goes with this 1.5K resistor up to +9. Let's find that. So here it is. Here's the 1.5K resistor. It's going up to +9 volts. And then it's also going to the input of the gain stage. So that should be going from pin 6 to pin 11 with a wire. So 6, 7, 8. So here's pin 6 is going over to pin 11. So let's see, 9, 10, 11. So pin 6 is going over to pin 11 with this blue wire. It's pretty hard to see. Okay, that was pin 6. Pin 7, 8, 9 are used for the NPN half of the push-pull. So pin 7 goes to pin 13. So pin 7 is down here. It goes up to pin 13. So there's like 13, 14, 15, 16. Yep. And then pin 7 also is my output. So, and you should see a scope probe there. Let's see. Yep. So there's a scope probe on pin 7. And then you should see a 10K resistor that goes over to this column. So there's a 10K resistor going over to this column. And then from there, there's a 1K resistor down to ground. So we have that. Here's a 1K resistor going down to ground. And then from the middle, from this column where these two resistors meet, there is this green jumper wire that goes back to pin 1, which is the inverting input. Okay, so that was pin 7. Pin 8 is the base of the NPN, so it's connected to pin 14. So pin 8, here's pin 8. So here's this blue jumper wire from pin 8 going over to pin 14, 14, 15, 16. And then we also have a connection from pin 12. I think I would have made it from pin 12 to pin 14. That's a shorter trip. So yeah, here we go. Here's pins 12 and 14 connected together with this blue wire up here. And then that's all that's happening at pin 8. And then pin 9 is the collector of this NPN half of the push-pull. It goes up to +9 directly. So here's pin 9. See this little red wire for power is going up to +9. And then pin 10, 11, 12 we don't use. That's the other PNP transistor. And then pins 13, no, that's not true. No, oh, scratch that. Duh. Okay, pins 10, 11, 12. Right. Here's pins 10, 11, 12. It's our gain stage. Oops. Okay. Pin 10. Pin 10 has this 300 ohm emitter resistor to plus 9. So let's find pin 10. So here's 9, 10. Yeah, pin 10. This is my 300 ohm emitter resistor going up to plus 9. Okay, right. And then pin 11 is its base. So there's a jumper from pin 11 back to pin 6 that's connecting the output of stage 1 to the input of stage 2. So there should be a jumper wire from 11 back to 6. So here's 9, 10, 11, and it should be going back to 6. Oh, I think it's this wire. Yeah. So here's, right, 9, 10, 11. So that's this blue wire is going back to, right, 6, 7, 8, 6. Yeah, so that's this guy. So this blue wire. Okay. Then, another thing that's happening at pin 11 is we have this capacitor whose purpose is to kill the high frequency gain. So it's 100 picofarads from pin 11 to pin 12. That's this guy right here. So this 100 picofarad capacitor. Okay, now pin 12 is the collector of the gain stage, this PNP transistor. So from there, we already talked about the wire from pin 12 to pin 14 for the output of stage 2 to the input of stage 3. There's this collector resistor. Now we don't have a 6K resistor in the kit, so this is a 2 3K resistors in series. So from pin 12, we have 2 3K resistors in series going to minus 9. So let's find pin 12. So 9, 10, 11, 12, right. Okay, so from there, you see here's one 3K resistor. It starts with orange. And then they make a connection in this column. And then from here, it goes down to minus 9. Okay, cool. So that's this, that's 12. And then, okay, 13, 14, 15 is the second PNP transistor. So that's the PNP half of our push-pull. So pin 13, it's connected, it's just wired to pin 7. So pin 13, so 13, 14, yeah. So here's pin 13. Here's pin 13. 16, 15, 14, 13. Yeah. Here's pin 13. It's wired back to pin 7 with this blue wire. Okay. And pin 14 is this base, so it's wired back to pin 8. Let's see if that's true. So, yeah, here's pin 14. Goes back to pin 8 with this blue jumper wire. Okay, and then pin 15 is the collector of this PNP half of the push-pull, so it just goes to minus 9. So pin 15, so here's pin 15. So it goes over here. I have another copy of minus 9 over on the left because it was kind of a hassle to come down here. So I went over this way and then down because I think in some previous version I was doing other connections to minus 9. So this comes over to here, and then from there it goes down to minus 9. That's good. And then pin 16 is our substrate pin, so it's also connected to minus 9. Oh yeah, so here's another red wire, and it's also going to minus 9 from pin 16. So pins 15 and 16 are both going to minus 9. Okay, that's all the connections. So, okay, the next thing I want to do is turn this into a times minus 10 inverting amplifier. And the way that looks is like that. So we have the input goes to 1K, which then goes to the inverting input of the op-amp, which then goes through the 10K feedback resistor to the output, and then the non-inverting input gets grounded. So the fun thing about that is you don't actually have to change any significant amount of wiring to make this happen. This just becomes the input signal, and whereas it was here before, and this becomes ground. Well, I guess this is still in plus. But this goes to ground. Okay, so we're going to take pin 5 and ground it. So pin 5 is currently going to our signal source. So instead, we'll pull that out. Instead, pin 5 is going to go to ground. So here, 1, 2, 3, 4, 5. Pin 5 is going to ground. Okay, and then our signal source is going to the bottom of that 1K resistor. That 1K resistor had been going to ground. So I will bring that 1K resistor over to a pin where I can make a connection. So let's bring it over to here. I'll bring it over here. I have to be careful not to touch things accidentally. And then we'll put our signal source there. Amazing. Wow, okay, you can't see what I see with the waveforms. But okay. So now we see that the output signal has the opposite sign of our input signal. That's what we expect for a minus 10 amplifier. And we still see the cool effect with undoing the crossover distortion on channel 2. But channel 3, the amplifier output, so right, channel 1 is yellow, which is the stage 1 output. Channel 2 is cyan or blue, which is the stage 2 output. Channel 3 is magenta or purple, which is the op-amp output. And then channel 4 is green, and that is it's multiplied by 10, and it's the input signal from the function generator. Okay, I don't think I have an easy way to flip that upside down. So you could see the size easily. Let's see. I don't know. Okay, I don't know how to do that. Oops. But anyway, you can see that the output is a little bit smaller than 10 times, right? So you see this would be, if the purple were just as tall as the green, because they're on 10 times different scales, that would be times 10. So you can see we have a little less than times 10. And again, that's because our open loop gain is not so big. It's only like 200 or 250. I don't know why it's not 480, but anyway, it's pretty good. So you can see the feedback. The feedback causes the ratio of output to input to be pretty close to 10, minus 10. So that's neat. So I think that's all we want to see. Yeah. All right. So that is the homemade op-amp lab. It's pretty cool. You can see that it takes a little bit of work to build it. It took me probably an hour and a half to wire all this stuff up the first time yesterday. Debugging, kind of, checking each stage, stage by stage, and just making sure the gains made sense at each stage as I went through step by step. So this circuit, you probably do learn a little more doing it in Circuit Lab than doing it on the real hardware. But if you do it on the real hardware, it feels very satisfying to make it work. So of course I did both. I did it in Circuit Lab and in the real hardware. If you're only going to do one, probably you want to do it in Circuit Lab. But it is really very satisfying to get it working in Circuit Lab, in the real hardware, and to see, you kind of made your own homemade op amp. It doesn't have a huge gain, but now you see, in principle, all the pieces that turn transistors into op amps. And previously, we saw how cool op amps are and how many neat, circuits we can build with op amps. So it's kind of neat to learn just enough of these bipolar junction transistor, like kind of idiomatic expressions, building blocks, that we then can say, okay, now I have enough pieces, I have enough understanding of enough of these pieces that I can see how we make an op amp. And again, the little idioms that we learned here: differential amplifier, current source, common emitter amplifier, and push-pull buffer. Okay, so that was Lab 17. See you next week.